Most of those detections came in the latest observing run. The sensitivity of detectors is increasing with every upgrade, which means that the pace, the speed at which we get those objects will keep increasing. And so in the next couple of years only, we'll go to tens of thousands of detections and eventually millions. Jest mi bardzo miło, jest to zaskoczenie, zaszczyt i frajda, żeby być tutaj dzisiaj. Mam trochę rzeczywiście slajdów, żeby powiedzieć o tym, co szczególnie mnie interesuje w astronomii, czyli o masywnych gwiazdach, w układach podwójnych i trochę o źródłach fal grawitacyjnych. I will switch to English. I do apologize for that. I still feel a bit more confident in English when talking about stars, but I'm working on that. And so massive stars are the stars that at the end of their lives, they collapse to become black holes or neutron stars. They're the most luminous, the most energetic stars in the universe that really stir the star formation in galaxies, produce some of the most energetic transients that we can observe to far away galaxies, and produce some of the heavy elements we have. And I think some of the biggest problems in the massive star community that we have now, the two of them would be, the first one is to understand the effects of binarity. So we now know that it's not very common to have a single massive star. Massive stars are usually formed in binaries, triples, multiple systems. And in those binaries, more often than not, a massive star at some point will interact with its companion by transferring mass and angular momentum. There are different types of mass transfer interaction, but they always have a very strong effect on the star itself, on the companion, on its final fate, and the role of a star in the universe. And so this, let's say, the trend to work on massive binaries came in the last decade, but it wasn't new to people. I mean, if you go back a couple of decades to the work by Bogdan Paczyński, this is some of the basis for understanding of binary evolution was formulated 60 years ago. And already back then, you can find sentences that show that people like Paczyński were aware that mass transfer interactions is probably one of the dominant effects on the evolution of massive stars, despite the much worse quality of observational data to back this. But after those early works, I think the trend to work on binary evolution kind of went down, and it took some newer results in the last decade to really spring it back up. And the second big challenge in the massive star community now is to understand the origin of gravitational wave sources. So what we observe now with LIGO, Virgo, and Kagra interferometers are merging pairs of black holes and neutron stars. When you put those compact objects together on an orbit, they emit gravitational waves so that they get closer and closer to one another until eventually they merge. And this moment when they merge is when they emit a particularly strong burst of gravitational waves that we can now detect with interferometers. And so far, after 3 observing runs, we have almost 100 detections in gravitational waves. Most of them are binary black hole mergers, but there is a bunch of neutron stars as well. And what's, I think, quite exciting is that this is kind of still the beginning. Most of those detections came in the latest observing run. The sensitivity of detectors is increasing with every upgrade, which means that the pace, the speed at which we get those objects will keep increasing. And so in the next couple of years only, we'll go to tens of thousands of detections and eventually millions, which means that pretty soon, the merging pairs of black holes and neutron stars will become the best measured state in the evolution of massive stars, which I think is a bit odd and a bit surprising to me when I realized that, because usually we think about observing stars when they're still alive, not when they have already collapsed. Something that's quite exciting about this is the context of the cosmological context of the entire universe, because even though we still observed sources that are quite local, they may originate all the way from the most distant galaxies. And this is because once you form a binary of 2 black holes or neutron stars, it may take a very long time for this system to spiral in and merge. And so even if the merger is happening in the local universe, those stars that might have formed the black holes might have been formed in very, very distant galaxies. And so this is something that we can probe in a way, but this is also complicating the picture when we try to understand the entire population of gravitational wave sources. Something that we often talk about here are formation channels. And what we mean by this is an idea of how to put two black holes or neutron stars close to one another. And they need to be quite close for the emission of gravitational waves to merge them together within the age of the universe. And so most formation channels begin with stars, which would then collapse to black holes. Another possibility are the primordial black holes that Professor Abramowicz talked about today. Then in primordial black holes, there is also the challenge of how to put the two of those black holes close to one another or to collide them, which might require dense environments. But the channel that I will talk about, potentially one of the key channels, is the evolution of massive binaries. And so the way this might look like, roughly, is that if you have a binary of two massive stars that are close to one another, they will evolve through a bunch of evolutionary stages. When the stars live, they will tend to expand at some point to become giants. If there is a nearby companion star, that will initiate a mass transfer interaction between the stars, producing some post-interaction objects, such as stripped helium cores of giants and so on. Eventually, one of the stars collapses to form a black hole or neutron star, and then the secondary, the roles reverse. The secondary may expand to initiate another phase of mass transfer, this time onto the black hole or neutron star, forming an X-ray binary, in fact, quite likely a super Eddington source with slime accretion disks that Professor Abramowicz worked on as well with colleagues. So those are all connected topics, really. And then this phase is thought to be quite important because the final binary, after all those interactions, whatever it is, it needs to be a closed system. So the orbital evolution during the mass transfer is quite key here. That is just one channel. There is a whole zoo of formation scenarios that have been proposed. So people have lots of ideas as usual. And I think it's quite likely that in the observed population of sources, we are seeing mergers that come from different channels already. And this really, this is quite exciting because those channels happen in different places in the universe. Some happen in the field. Some of them are postulated to happen in the centers of galaxies. The others would only occur in very dense stellar environments. So in principle, it's nice to be able to probe all of those places in the universe with gravitational waves. But this also increases the challenge when you try to combine all of this together. Your model for the population becomes extremely complicated. And we are already sort of hitting this challenge. This is, you cannot probably see it very well, but the idea of this figure from the review paper showing the sort of state of predictions of population models for the formation of LIGO-Virgo sources. So what's happening on the x-axis is the predicted rate of the LIGO-Virgo events from a given channel. And the lines are color-coded according to the type of the channel. So the binary evolution is in the green. But what is interesting is the scale on the x-axis. This is a couple of orders of magnitude uncertainty in our predictions. In the case of isolated binary evolution, this is about 5 orders of magnitude. And this is kind of a problem. We now have almost 100 detections. A couple of years back, if you asked us what would we do with 100 detections, we would say we'd solve everything. That's amazing. But we are yet to, because of those uncertainties, we are yet to give robust conclusions regarding the evolution of massive stars or the origin of gravitational wave sources. And it's not completely clear whether having 100 times more detections would help. And this is not a good situation because we'd like to justify having more detections with future detectors. And so I think a question you might ask is, how come we are so bad at this, having so much uncertainty here? And so I will focus again on the binary evolution channel and discuss some of the major uncertainties here, which I think are related to the process of the formation of black holes and neutron stars. That's the challenge for most of the channels in general. but also in the processes related to the mass transfer interaction between the stars. And this is important not only for the gravitational wave sources, but for massive stars in general. And so we distinguish between stable and unstable mass transfer evolution, which I'll talk about in a second. Unstable mass transfer leading to so-called common envelope. And the idea of common envelope is the following. When you have a binary system and one of the stars expands so that it starts to transfer mass to its companion, in some circumstances it might happen that this star keeps expanding with respect to its orbit so much that it will essentially engulf the entire binary system. It will be as big as the orbit itself, so that the companion star is essentially moving throughout the medium of gas now, whether it's a black hole or another star. And when it's moving through that envelope, it's experiencing drag force, which is slowing its orbital movement, so it's spiraling inwards closer to the core of the giant. This process of spiraling deposits energy into the envelope, and when you put energy into the envelope of a star, it usually tends to expand. When the envelope expands, the density drops, so the spiral end slows down. And if you put enough energy into the envelope, chances are that the spiral end will stop entirely. And so you will end up with a closed binary composed of a core of the giant and the companion star, and most of the envelope being ejected to far enough to not make a difference. And so this idea, as many things in astrophysics, was coined by Paczyński, and usually the reference here is a conference proceedings, but Paczyński himself cites the communication with others, with Webbing and Ostriker. It's quite often that various ideas are discussed in the community before they get published. And I mean, this has been almost 50 years ago. Many people have worked on common envelope evolution. It's important for various sources, not only the LIGO, Virgo, Kagra ones. It's a huge numerical challenge to solve because of the huge range of temporal and physical scales. And most of the evidence for common envelope evolution we have, constraints from observations and simulations, is in the regime of white dwarf progenitors, so lower mass stars. A bit more in neutron stars as well, but in the case of black holes, it wasn't studied so much. And so this is what we try to understand a little bit. I mean, if you take a step back and try to think about order of magnitude estimates, if you want this in spiral to stop, then you need to put enough energy into the envelope to unbind it to infinity, let's say, times some parameter, because quite likely you lose some energy in the process, or you are not able to transfer all of the orbital energy into the envelope. And so what we did here is trying to be quite optimistic, saying that we include all the energy we can think of, roughly, and that there's no energy losses. And based on that, and calculating the envelope binding energies of different types of massive supergiants, we then ask a question, okay, what type of black hole binaries with massive giants can survive this process, meaning stop the in-spiral? If you don't stop the in-spiral, then the black hole continues to spiral inside the helium core, and exciting things happen, but it's quite unlikely that the end product is a binary black hole. It's probably a transient or a Toruniu object. Okay, and so the result of this exercise is shown in this figure, where the parameter space for where the common envelope ejection is possible. This is an HR diagram. The parameter space is shown in green. So those are the type of donor stars, type of giants that you can put on a binary with a black hole, and their envelope is so loosely bound that the in-spiral can eject it. So all those stars are red supergiants with really loosely bound envelopes. I mean, those are stars, when you perturb them on the surface, it's quite likely that part of the star would just fly away, which might be the reason for eruptive mass loss from those type of stars in general. There are a couple of problems here in the context of LIGO Virgo sources, because we don't really observe red supergiants coming from stars more massive than initially 40, 30, or depends on who you ask. So it might be that stars above this mass range never become red supergiants, which puts in question the common envelope channel, for binary black hole mergers. We need stars this massive to work because we see quite massive black holes in gravitational waves, more than 30 solar masses. Something interesting to point out is that the common envelope evolution is associated with luminous red novae, which are optical transients, very cool, dusty transients. And their association with stellar mergers or common envelope evolution in general was actually found here in Toruniu by Romuald Telenda and Noam Soker and later others. And this comes from observation of a particular binary system where we could see that the orbital period is steadily decreasing until an eruption, a transient, a luminous red novae. And that's a very nice smoking gun signature that stellar mergers can lead to those sort of transients. All right. So I was talking about the common envelope evolution a bit, saying that it might not be so effective for the formation of those massive binary black hole systems that we see in gravitational waves. And so it might be a time to focus on the stable mass transfer evolution instead. And so, again, if we take a step back and try to think about, in general, what the mass transfer does to stars, then usually the picture is the following. The interaction is happening when one of the stars is a giant, has a core and the envelope. And what roughly is happening is the mass transfer strips most of the envelope, reveals the helium core that was processed in nuclear burning, and we end up with a stripped star, or Wolf-Rayet star, depending on the mass, or a subdwarf. And the companion, because if it accretes a bit of mass, it quickly gets spun out to fast rotation. It may be even a critically rotating star that is spitting mass from its surface because the centrifugal force is equal to gravity around the equator. So those are stars we call BE stars. And in general, that process is one that carries most implications for how binary stars are different from single stars. It's going to have an effect on the nucleosynthesis of stars, their final fate, their appearance, and the binary orbit itself, which is key for the evolutionary channels. So we have some ideas on how this can work or what the effect this has on stars, but as usual, it's easier to have ideas. It's more difficult to test them. And the best way, perhaps, to do this is to find binary systems that just went through mass transfer. And we can observe and measure those stars. We can observe and measure the orbits, and then check our theories. And so what we should ask ourselves is, how do these look like? Yeah, what are the properties of those stars? And so here's an example of how a mass-losing star looks like in a nature diagram, so its temperature and luminosity. It's going to evolve through the main sequence. At some point, it reaches the mass transfer phase. Its luminosity drops down because most of the energy is captured in an expanding envelope. The mass transfer itself is very short. It's a couple of thousand years. We're not that likely to observe the binary there. After the mass transfer, the system detaches. So we've transferred most of the envelope. There is some remaining hydrogen on top, but the star is now contracting. This is thought to be a relatively quick phase. And then finally, where we think most of the post-interaction binaries should be, is where we have a stripped star, mostly a helium star, which is compact, it is very hot, and it's rapidly spinning companions. So in principle, this is where we should be looking. The trouble is that because those stars are very hot, they emit most of their light in the UV. And so this blue here is the spectrum of a stripped star. And it's compared to the synthetic spectra of a couple of possible companions. And what's happening in the optical bands, that's that usually the companion really outshines the stripped star by a lot. So we would need to go to far UV to see the stripped stars clearly, and this is expensive observation. And because of that, the stripped star binaries, or this type of post-interaction systems, they had escaped detection for a long time, even though they had been predicted to be very numerous in stellar populations. And so this took so at this point, this paper is by Ylva Jordberg, and the idea was coined to have a catalog of stars in the UV to find UV access to stars that we see in the optical, and maybe that's a signature that this star is actually a post-interaction binary and not an ordinary star. This still took a couple of years, but we finally have the first detections of stripped stars binaries. So those are the post-interaction systems pretty soon after the mass transfer itself. The binary properties of those systems are still to come, and this is where we are going to get nice constraints for our evolutionary channels. But something else happened in the meantime. We started detecting binaries such as this one, where, I mean, in principle, okay, we just have a primary and the secondary. In principle, it seems like two similar stars of about 16 solar masses. But when you take a look at the properties measured from the spectra, then indeed the surface temperature, luminosity, and radius are similar, but the surface gravities are not, which means that one of these stars is about 3 to 4 solar masses, even though it looks like a 16 solar mass star, and the other has about 16 solar masses indeed. And so when you try to make a model for this to match most of those parameters, then what you get is that it is actually a post-interaction system that we somehow caught during this contraction phase, really soon after the mass transfer. So the stripped star is currently moving through the HR diagram to the left. It's contracting. And so it's overlapping with the main sequence. At the face value, it looks like an ordinary star, but it really isn't a normal star. And so this binary is the one with this, what we call a puffed-up stripped stars, meaning that this residual layer of hydrogen, there is some burning in there, and that makes the star bigger. And so it's really puffed up, meaning it's bigger than just a normal helium star. It's still a bit inflated. And the companion is rapidly spinning a binary. And so this is one system, but it's already showing that we need to revise our models for accretion because the companion accreted so much in this binary, and it's almost critically rotating. It means that the stars have to have some way of keeping accreting mass, even though they are close to critical rotation. Or perhaps the accretion happens a bit later. There are various ideas, but it's already clear that we need to have some revised models for mass transfer interactions. And so this is one system, but turns out it's not the only one. Over the last year or two, there was a bunch of binaries found in this stage. So those are the puffed up cool stripped star systems. Yeah, the mass losers are overlapped with the main sequence. Those are the hot stripped stars. Those are the ones that people have predicted for a while and that were finally found in the UV or in the optical if they're low mass enough. But we are discovering those puffed up ones. And this is a bit surprising because classically this phase should be really short-lived, the thermal timescale, which means that in the case of massive stars, that's a couple of thousand years, and we shouldn't really see anything like this in the SMC, which is the Small Magellanic Cloud. It doesn't have enough stars to statistically see these. But it turns out that the lifetime of this, this is, on the y-axis is the lifetime of this puffed up stripped star. It's actually 100 times longer than just thermal timescale. What's happening in those stars is that the hydrogen shell burning is keeping the envelope inflated for quite a while, depending on how much of the envelope is left, what's the metallicity of the system, and so on. And from this comes a prediction that about 1% of all the OBA stars also overlapping with the main sequence, even though they look like normal stars, they're actually post-interaction binaries right after the mass transfer. A lot of them should be in the data, but we are now sort of on the quest to find them. And the duration does depend on the metallicity, because in the more metal-poor stars, there is usually more envelope left, and the envelope is also not stripped so quickly via stellar winds. But in fact, if you play with your model assumptions a little bit, what we found is that at the metal-poor stars of the Small Magellanic Cloud, but even characteristic for a more distant universe, massive stars, this duration of the contraction phase can be up to nuclear timescales. And the reason for that is that what sometimes happens in those HR diagrams that I was showing before is that the mass-losing star never contracts to become a UV bright, compact helium star. It might be that it has so much of the hydrogen left that it's not able to burn through this until the end of its evolution. And so it will never really show its colors as a star that's strongly affected by binary evolution. It will be not that different from a normal single star. And this is a bit concerning, because if you want to think about the influence of massive stars in the more distant galaxies in the early universe, where most of the stars were like this, had the lower metal content, then we'd like to understand actually what are the temperatures of those stars, how much ionizing flux they produce and contribute to ionization of the universe, and whether all those effects of binary evolution apply to those stars indeed. And so we have a prediction that perhaps if we go to the Small Magellanic Cloud, go to the most luminous and massive stars there, and try to see if there are any what we call partially stripped stars, for lack of a better word, there that we wouldn't expect otherwise, then that's one way to start to test this. But okay, coming more generally and towards the end of this, the overall prediction we have is that quite a few of stars on the main sequence should be post-interaction binaries. 1% may not sound like enough, but it's enough star on the main sequence to find them. What you need to identify is multi-epoch spectra, because those stars in this binary are usually of a similar spectral type. So the lines in the spectra are overlapping. So you need some pretty good quality of data to see the lines moving in radial velocity curves. But there is a lot of data that's already there, actually, and that's also coming in the future with the spectroscopic surveys in the Small Magellanic Cloud in the context of that low metallicity, but also in the Milky Way. I mean, from the collection of a couple of different programs, we might be getting tens of thousands of massive stars with good quality spectra, and those type of numbers in the massive star community are really extreme. We usually deal with maybe hundreds of stars, not tens of thousands. And so this is pretty great. And one byproduct of having the spectroscopic surveys is that when you look at the binaries, you can also find situations when your star is moving on an orbit, but you don't see the companion. And some of those binaries may be systems when the companion is a black hole. Such systems were found recently, 2 of them, 2 binaries where there is an unseen massive companion of a few solar masses interpreted as black hole. The primary, the moving star, is quite a massive star. Those are O-type stars, about 20-something solar masses. They're really in the progenitor range for LIGO, Virgo sources. There may be quite a few more, tens to maybe 100 more hiding in the SMC and in the Milky Way in the data that's being taken or scheduled to be taken. So there is a chance for a lot more black hole constraints, as well as post-interaction binary constraints. And finally, you can find those black hole binaries for astrometry by observing the actual movement of the companion star in the sky, also from microlensing. But this is something that Łukasz Wyrzykowski will talk later this week. But having constraints on the mass function of dark compact objects in the Milky Way will not only constrain the presence of primordial black holes, like Professor Abramowicz explained, but also although more conventional evolutionary channels for LIGO Virgo sources. And so wrapping up a little bit, as a summary, I think the takeaway for me from all this is that we now are at the stage where we need to find solutions for how to deal with the amount of gravitational wave data that will come very soon, actually, how to take the best advantage of this to use gravitational wave astronomy to study stars. And I think that gravitational astronomy and stellar astrophysics should go hand by hand in this. It's not necessarily what's happening when you go to gravitational wave conferences. There's not really stellar astronomers there. And on the side of massive binaries, mass transfer, I think, is one of the key uncertainties, but there is lots of data coming to constrain this. And I really wanted to say thank you again, but I wanted to point out that I think people like me from this generation, we are very lucky to be doing this now, because thanks to all the nice surveys, the gravitational wave astronomy being born, and also something I didn't mention, or that actually I use usually, is the Stellar Evolution Code, MESA, which is now the first open source ever Stellar Evolution Code, which is a bit of a game changer. It's no longer that there is some tool that the, excuse me, that the team is using that you don't quite know how it works. It has hundreds of users across the world, including in Poland, as well as developers. Radek Polecki from CAMK is one of the developers. I'm sorry, Radek. Radek Smolec. Radek Polski is maybe a future developer. But no, I mean, really, I think it's quite unexpectedly, because stellar astrophysics is an old, I think, field. It really feels like a renaissance of stellar astrophysics, and it's really great to be doing this. So thank you once again. Dziękuję bardzo.